Distance to the mean classifiers are classifiers that predict the class of the group with the nearest mean. The idea here is that for each class, we will find the typical sample. We will find the average sample, hoping that that sample will be super representative of each class. So then when we receive a sample for evaluation, we calculate the distance between that sample and all the means for each class, and then we identify which one is closest, and then that's the class that we assign to the evaluated sample. So what variables are involved within this classifier? In terms of hyperparameters, we just need to define the distance metric. So what type of distance metric are we going to use? Is it Euclidean, Mahalanobis, etc., etc.? In terms of parameters, so the values that the model can learn automatically from the training data is just the training data itself. Either that, or we save the class means. Now, if we only save the class means, then continuous learning, so the ability to add more information to the model as we receive or as we obtain more training data, gets a little bit more complicated. It can still be done, but as I said, it's a bit more complicated. So what type of decision boundaries do distance to the mean classifiers build? Well, if we're talking about binary classification, then the decision boundary is going to be a straight line. So it's going to be a linear classifier because we only have two samples. If we have we only have two classes. So we're building that based on two samples, one for each class. If we have more than two classes, then it's not going to be a linear decision boundary, but it's going to be a relatively simple decision boundary composed of straight lines. And then one needs to wonder whether defining a class by its average makes sense. And this will depend on the problem and on the data at hand. In this scenario now, in the one represented in the figure, in the slide, potentially, especially for the circles, defining that class by its average doesn't make much sense given how the samples are distributed in this space. And also, nearest distance classifiers cannot account for interrupted, say, or discontinuous some classes. So in this case, the triangles seem to have two regions. Nearest distance classifier can't account for that at all. So in terms of what are the advantages and the disadvantages of this classifier, well, it's a very intuitive and straightforward concept. I mean, it's just, we can think this as just looking at the stereotype sample for each class and using that stereotype to make our prediction, our decision on an evaluated sample. It's a very easy to implement and to use. The training process is super fast because effectively we only need to, save the training data and potentially calculate the average sample for each class. And then the validation process is also very fast because now we just need to calculate the distance between the evaluated sample and each of the classes. So in the case of two classes, that's only two distances that we need to evaluate. However, they can be memory intensive, especially if we are saving the whole data, which, as I said, has advantages in terms of it allows for easier continuous learning. And if we have a lot of training data, Again, this is going to be memory expensive from the memory point of view. It's going to be sensitive to outliers because, as we said, especially if it's based on the average, we could potentially base this on quantiles and then make it, so on the median, and then make it robust against outliers. But again, it will require modifications of the original algorithm. And then the decision boundaries, as we saw, are very simple, and it begs to ask ourselves whether defining the classes or a given class by the average sample makes sense or not.